This is part one of a series that I'm starting called Connected Particles, where I'm going to go over every question, maybe every question, probably every question of a worksheet that I saw online from a website called Madass Maths. I'll leave a link to it in the description if you want to have a try, if you want to try some of the questions before I do. Anyways, yeah. So I'll do five questions per part, hopefully. Question one. So we've got this kind of system going on. We've got particle B, and it's got a mass of 9 with having a mass of 5, all in kilograms. This is like going to be the most important thing that we're going to be using throughout most of these parts, and also this weight equals mg. You should know both of these. This is Newton's second law, and then this is just weight equals mass times gravity. Gravity we'll just call g, and mass is just whatever the mass is. So for A, it's going to have a weight down of 5g, and obviously weight is a force, okay? So the force acting down on A is 5g, 5 multiplied by gravity, which will take us 9.8, but we'll do that later. And then for B, it'll be 9g. Okay, and they're 1.75 meters above the ground, and where this is the bottom, we'll say. And then it's released, the entire system is released from rest. So you can imagine that B will go down because it has a greater force downwards. So there's a resultant force acting down here, or in other words, a net force. In the resultant motion, B reaches the floor before A reaches P. Okay, so by the time this is at the floor, this doesn't actually touch the top, which is what it's saying. We want to calculate the tension in the spring. Okay, so there'll be tension here, and there'll also be tension here. Okay, so whenever you've got like a rope or like a string or something like that, and it's taut, it should say somewhere that it's taut. And if it doesn't, well, it definitely is. I don't know, somewhere there. But anyways, the string here is taut, so it's not slacked. Okay, so there will be some pulling force on it, which is just tension. Okay, so we can say the resultant force at B maybe is 9g take away that T, because this T is acting against the downwards resultant force. What else is it? Oh yeah, there's also 3.5 newtons of air resistance. This will be acting down A, but it'll be acting up on B, because as B is moving down, air resistance will be acting up, obviously. And when this is moving down, this is moving up, so air resistance will act down on this one. Okay, so if we forget B, let's just look at A for now. A is going to be moving up, so this force T is going to be greater than both of these. So the net force on particle A is T minus 3.5 minus 5g. Okay, and it needs to equal its mass times acceleration. So its mass is 5 kg, and acceleration we'll just call A. So this equals 5a at A. Now at B, you'll have, instead of T being the larger force, it's going to be 9g because it's going down. Okay, so the resultant force will be greater, it will be acting downwards. Okay, so it's 9g, take away 3.5, take away T. That's the net force, equals its mass 9 times acceleration A. Okay, and because both of these particles are connected, they're going to have the exact same acceleration. So if we rearrange for A for one of them, we'll just say this one here, and put it into there, you can calculate T, which is 64. Determine the speed with which B strikes the floor. Now, there's a couple of things here to notice. First of all, you might just think, oh, well, it's just double this height, because by the time this has gone down 1.75 meters, this will go up 1.75 meters. But the question says, oh, no, never mind, sorry, I'm thinking of a different question, yeah. So for this, we're going to be using one of the Suva equations. I don't know why it says T equals 64 up there. Just ignore that. We're going to use one of the Suva equations. We don't have time. This is the only equation that doesn't give us time, so we'll use this one. The final velocity of B will just be, well, we don't know what it is because that's what we're looking for. Its initial velocity is 0 because it was released from rest. Its acceleration, we know what that is. I'll get to that in a second. And its displacement, so the amount that it's moving, is 1.75 meters. Okay, and so that's that. We also have that 9g take away 3.5 take away T, but now we know that T is 64 equals 9a. So rearrange for acceleration here. Just solve that. G is 9.8, obviously, that's just gravity. So we get acceleration is 2.3, so we plug that into there, and then just get V is 2.4 meters per second. Obviously, taking the positive solution, you probably won't have to take the negative, but it depends on which direction you've called positive and which direction you've called negative. two blocks of masses 4 and 6 on a smooth horizontal plane surface. The fact that it's smooth tells us that there's going to be no resistance, no friction between them and the ground. Two forces F and N, 30 and 5, 30 and F, acting on the system has a constant acceleration of 2 meters per second squared. So there'll be tension here in the string, or rope, or whatever it is. Okay, as always, there's always going to be tension whenever you have a string that's taut, and say if it's not taut, it'll have a thrust force, because it'll be a pushing force instead of pulling. F equals ma, again. If we have a look at, say, this one here, it's going, let's just say it's going to be moving right. It doesn't matter. Does it tell us? They're moving in opposite directions, and they're just, okay, the system has a constant acceleration, and there's two possible values for F. We'll just assume it's moving right for now, and then later on we'll assume it's moving left. So we'll assume this is positive 2 meters per second squared, so that this is going right. So this is 30, take away t. Oh no, sorry, we're having a look at the full system right now. So of the full system, it's 30, take away t here, plus t, and then take away F. And the reason why I've done that is because the tensions cancel out, so you can just ignore them. So you only have 30 take away F equals the mass, which is 6 plus 4. So the total mass, because we're having a look at the full system, 10 multiplied by the acceleration, which is 2. So this force here must be 10 newtons. Okay, and then also here, if we're saying that this force is 10 newtons acting that way, the tension here must be T take away 10 equals its mass times acceleration. So T take away 10 equals 4 multiplied by acceleration, which is 2. To rearrange for T, which is 18 newtons. Now, we just said that this acceleration was acting in the right direction, so like to the right, but it could be acting to the left, and we don't know what's happening. So now that we've assumed this, we've got a pair of answers, because it says there's more than one possible answer for F and T. So we've assumed A to be positive. Now let's assume it's negative. So let's basically assume that we're going to the left. The entire system's moving to the left, and if we do that, we can do the exact same things up here, looking at the full system, but we'll just take acceleration A to be -2. So we'll do 30 take away t plus t. So these cancel, take away F, which is just 30 take away F, equals the mass 10 multiplied by the acceleration, which is -2. Get F to be 50, and do the same thing over here. So this will be t take away 50 equals 4 multiplied by -2. So you get t as 42 newtons. Two particles A and B, so mass is 3 kilograms, m kilograms, so this force acting downwards is 3g, and then this one here is mg. The displacement off the ground is 1.28 meters, and we've got tension in the rope here, which we'll just call T, and B is accelerating towards the ground 1.96 meters per second squared, while A never reaches P. Okay, that's good. F equals ma, obviously. Now, we'll have a look at the full system again. So, and the reason why we'll do that is because obviously we can cancel the tensions again. So if B is moving down, we have mg take away t. Okay, but on this side it's plus t, because this is greater than this force here, because this entire thing's moving up. So it's mg take away t plus t, so these cancel, and then take away 3g to get the net force for the full system, which is just mg take away 3g, and that equals its mass. So 3 plus m multiplied by the acceleration 1.96. We know what g is, 9.8. Rearrange for m to get 4.5 kilograms. So it looks like I've actually done part B before part A, maybe because that was just easier. For the period before B reaches the floor, calculate the tension in the string. Okay, now I know what m is. I can just have a look at, say, this one, or I could have a look at that one. It doesn't really make a difference. Which one did I? Oh, I went for A. Okay, so you can see that T take away 3g is the net force, equals its mass 3 multiplied by acceleration, which is 1.96. So you get T as 35.28 newtons. Calculate the speed with which B strikes the floor. The acceleration is constant. It says somewhere here. No, it doesn't actually say, I don't think. It probably says that somewhere. But this is constant acceleration, so we're going to use suvat. Okay, we don't have time, so we're going to be using this equation again. Okay, the final velocity, we want that, so we'll just call that v. Instant, current acceleration, or the initial, is 0 because it starts from rest. Acceleration is 1.96 and its displacement is 1.28. So put that in free range for v, which is 2.24 meters per second. When b reaches the floor, it remains at rest. Determine the greatest height above the floor reached by a. Sorry. This is what I was on about with the first question when I got confused. I thought I was actually doing this question instead of question 1. The thing here is, you might just say, well, if b goes down 1.28 meters, and that must mean that a goes up 1.28 meters, and because a is already 1.28 meters above the floor, so it'll go at 1.28 plus the 1.28. So the answer is 2.56 meters, but that's not the full answer, because it says the greatest height. So you can imagine that when b drops down and hits the ground, it kind of like tugs on this just a tiny bit. So you can imagine like a reaches up here, so it goes up 2.56 meters, okay, and then it bounces up just a little bit because b's hit the ground, and then b goes to rest, and then a drops back down that small distance that it went up. If we have a look, say at b, we can say its final velocity, because it's at rest now, is 0. Its initial velocity was 2.24 as we've calculated, and its acceleration is just a, and its displacement is s. Okay, but if you imagine this velocity was referring to a moving upwards. Is it? Oh no, sorry, never mind. Yeah. So yeah, carry on with that. But this where is it? This acceleration here, it's actually going to be minus 9.8 newtons because first of all, gravity 9.8 newtons acts down, but A is moving up, so it's moving against gravity, so it's moving minus 9.8 meters per second squared up. So we can take acceleration to be minus gravity. Okay, so we'll just put A as minus 9.8 in to get displacement as 0.256. Now, this 0.256 that's the little tug that pushed it up that small bit, because you can imagine it already moved up 1.28 meters. And so it already moved up 1.28 meters from here, and then plus that small tug, which is this. But obviously it's already 1.28 above the floor, so it moves up 1.28, and then another 1.28, and then that 0.256. So this add this is the greatest height it reaches, which is 2.816 meters. This is what I saw in the mark scheme. Not in the mark scheme, but say in the solutions part. The person, this diagram is actually pretty good, but say this is the original position of A and B, and as B reaches the ground, A goes up that same distance up, and then it's like tugged up a little bit as B hits the ground. Okay, so it goes up 1.28, then 1.28, then 0.256. Here, so we've got two particles, 2 kilograms, 5 kilograms. So this way acting down here is 2g. And then just one thing that I'm going to do here is I'm going to split this up into its vertical and horizontal components, where the vertical component is perpendicular to this plane here, this horizontal plane. So if we draw a line going down here and then another one going like this, we can split this up. And this here is actually going to be 2g cosine theta, and this here is going to be 2g sine theta. And the reason why that is if I draw a triangle here just to like show you, this angle here is actually going to be 30 degrees. First of all, we know this hypotenuse here is 2g because that's just this diagram, and then this angle here is going to be 30 degrees because we've got co-interior angles here. So 180 minus 30 will give us this angle here, which is 150. We already said that this vertical component was perpendicular to this line here, so the angle here of 90 degrees. So you've got 90 degrees here and you've got 150 degrees here. And so if you do 180, take away 150 plus 90, you'll get 30 degrees. You get 30 degrees just there. Okay, so you've got 90 on this side, 150 on this side. You know, it's a straight line, so it's 180 degrees. So this here must be 30 degrees. And if you have a look at SOHCAHTOA, okay, if we say we're having a look at, if we call this length here x, okay, well, what is sine? Sine is opposite of a hypotenuse, so x over 2g is sine. Okay, but that also means that we can say that x is just 2g sine 30. Okay, so we can call this length 2g sine 30, in other words, 2g sine theta, because that theta there is just 30. Okay, and similarly, I've just put on the tensions there, and yeah, and similarly for so we can just say that's that, and then say if we call this y, and we just say that well cosine is just adjacent over hypotenuse, so y over 2g. Okay, we can say that y is just 2g cosine 30. Okay, so we can just replace this with that, and now we've also figured out that this here is just 30 degrees, so we'll just plug that in. Okay, so we've got that set up, we've got this set up. I'm not going to go over this triangle thing again because it just takes too long for me to draw out and things like that. And so I'm going to go over longer explanations in like the first part or two maybe, just to like get you you know, confident with some of the stuff that I'm doing, so that I can like kind of gloss over it really quickly in their later parts because I don't have the time to be spending on that, to be honest. Anyways, here, so sine 30 degrees is just a half. So half times 2g is just g. And then here, this is just root 3g. Okay, so we can replace that with that. What else? So we've got the coefficient. Okay, no, before we have a look at that, there's a normal reaction force acting up from A. If you just remember, you know, I'm sure you did physics at GCSE. You do know that, say, if you have like a desk and you have a desk, if you have like a book on it, there'll be a normal reaction force acting up. It's not Newton's third law, but actually the forces are equal and opposite. So this here would just be equal and opposite to this root 3g. So you've got a force here acting upwards, that's root 3g, and that's just a normal reaction force. Okay, and then here we've also got a 5g, which I didn't put earlier for some reason. We've got friction, because this is a rough plane, it says somewhere. Yeah, so fixed rough plane. So we've got friction here, and friction is just written as mu r, where r here is the normal reaction force, which is root 3g, and mu is just the coefficient of friction. We're told that the coefficient of friction is a half root 3. Okay, so mu is a half root 3, and r is just the normal reaction force. So mu r, or the frictional force, is just half root 3 multiplied by root 3g. Which just gives us 3 over 2g. So you can just replace this here with 3 over 2g. Now, F equals ma again. Let's actually get started, because that entire thing there was just setting up the question. Calculate the tension in the string immediately after the particles are released. If the particles are released, this has a greater mass than this one, so this is going to be moving down. And this here will be moving upwards like this. Okay, so if we have a look at A, and we just have a look at resolving the forces in this horizontal, in this like diagonal direction, we can say that T minus this G here, because this G is acting in that same parallel direction, but in the opposite way. So it's T minus G minus 3 over 2G as the net force. And that equals mass times acceleration, where the mass is 2 and acceleration is just A. We don't know what that is. And then at B, this is moving down. So this is going to be 5G take away T equals 5 multiplied by A. Now, because these two are connected, they're going to have the same acceleration, because whenever two particles are connected, they have the same acceleration. So just rearrange this one for A, and then plug it into there. And then where G is 9.8, obviously. And then just rearrange for T to get 31.5 newtons. Is that the entire question done? Yep, I think so, yeah. This is the last question of this part. Particles A and B. Mass is 3 and 7 kg. So downwards force here of 3g, and then here of 7g. The vertical component here, perpendicular, you can just draw that in like that. This will be 7g to sine theta, and then this will be 7g cosine theta. And we've got a normal reaction force upwards of 7g cosine theta, obviously. Tan theta is 3 over 4. So I'll get to that in just a second later. The coefficient of friction between the box and the plane is 0.6. Okay, so there's frictional force acting backwards up here, and that's 4.2 g cosine theta. Okay, it's mu r, where mu is 0.6, and then r is this. So 0.6 multiplied by this. Okay. Okay, now I've also gone over one thing. One thing that I didn't actually write here. Well, actually, I'll just edit it in. Oh, never mind, I have actually put it in. Yeah, so I said that this is 4.2 g cosine theta, and I'll get to that in a second. first of all, let's just write the tensions in this. Okay, but if we're saying that tan theta is 3/4, so and this angle here is theta, you know, by the same way that, you know, you can just angle chase to find this. So we said that this here is theta, and then the opposite of a opposite over adjacent is 3, 4, and this is a 3, 4, 5 triangle, and that means cosine. That means sine theta is 3/5, and cosine theta is 4/5. Okay, and so you can just replace cosine theta with this here to get 4.2 multiplied by 0.8. Apologies for that. I just had to edit that part out. I did realize here, I was like, where did I actually get that random number from? Because it was actually incorrect, and I just forgot to edit it because the first time I did this question, I incorrectly wrote this part here and I forgot to change it. But anyways, let me just skip back forwards to all of this. So this is just 0.6 cosine theta, 0.6 g cosine theta, where it's the coefficient of friction 0.6, which is mu multiplied by r here, and r is 7. So sorry, so this should actually say 0.6 times by 7 g cosine theta, not that. It doesn't matter. I mean, I've explained it now, so you should know. So this actually says 0.6 multiplied by 7 g cosine theta. Okay. We know what cosine theta is. It's 0.8. So 0.8 multiplied by 0.6 multiplied by this imaginary 7 here multiplied by g, we'll get a 3.36 g here. We can also replace all of these because you know, we know what they are. So we'll just do that. Okay, and I can just get rid of that. If we have a look at A now, here, A is moving down because it's the entire system's released from rest, and so you know, this is just moving down. This is 3g take away t as the resultant force acting down equals its mass 3 multiplied by the acceleration a. And then at B here, I'm going to have a look at this direction here, and so we'll have t take away 4.2g take away 3.36g as the resultant force equals its mass 7 multiplied by the acceleration a. They're connected, so they have the same accelerations. So you know, you can just rearrange for a here and put it in there. I didn't do that because, see, we're looking for the tension and we want the acceleration. So we could just rearrange for a and put it back into there and solve for both of them. So that would work perfectly fine. But what I did was I added these two together so I can cancel out this t and this minus t. And so you'll get this. And then where g is 9.8, so collect these together, put 9.8, and get acceleration as 3.76 meters per second squared. And then I put this back into that one. So it's just another way of solving simultaneous equations. G is 9.8 again, and the tension is 18.1 newtons. And that's the full question, I think. Is it? Yep, so we've got the acceleration, we've got the tension. Yep, that's everything. Thank you for watching.